Hello, in this video we're going to look at and derive the asymptotic confidence interval for the difference between two independent population means. Here we're not assuming that our populations are normal, and so this is it's an asymptotic result, and we'll prove this in this video. So here in the video we have to assume some things. We want to assume that the x's are IID with a mean and a variance, and the y's are IID with a mean and a variance. And actually the y's and the x's and the y's are independent from one another. I don't have that written down, but it should be. And then this next assumption is, since it's asymptotic, we want m and n to go to infinity in a certain way, in such that it's well behaved. And the way we're going to do it is we have the constants all divided by an m or an n, and we're going to set it so this converges to a constant alpha. So as m and n go to infinity, they do it in a manner that is well behaved. Now this is not needed in the derivation, but it sure does make it easier. So I'm gonna show this proof in this, or use this assumption in the proof of this video. So now by the central limit theorem, we know each of these converge to a standard normal. So that's given. Now let's look at this ratio. So this is the standard deviation for this, the difference of these, the difference of the means. So that's how we get this. So then we take it over each set. So we move the x over and the y over, and we get this. So now this quantity, what we do is we multiply it by 1. So sigma x squared over m. And then this is the same thing. It's sigma x over square root of m. These two quantities are this, we're just multiplying and dividing. And then we do the same way here. We set this aside and we multiply and divide by this quantity. So we're not changing the the quantity. It's a well chosen one. But this right here is what we defined as alpha, mn. So, and then of course we want the square root of it. This comes down, the minus, and then this is 1 minus alpha mn. And then this comes down. Now the reason we do that is this converges to a constant, and then this converges to a distribution. So we can use Slutsky's theorem on this to say that this piece converges to alpha times a standard normal. And we can actually do the same. So if we forget this side, this converges to a constant, this converges to a distribution. So we use Slutsky's theorem to say that this piece converges to, this, where this is a standard normal distribution. Now, since this piece and this piece are independent from one another, we can use the continuous mapping theorem to say that this difference converges to this difference. And this is just a combination of standard normal random variables. So this is normal, but we got to figure out the mean and the variance. So if you take the expected value of both sides, you get 0, and then the variance would be this squared plus this squared, and it ends up being 1. So this quantity converges to a standard normal. That would be this quantity. So let's move on. So now we've established that. So we're not going to prove it, but I have a video showing that the sample variance converges in probability to the population variance, and that's true for both the x's and the y's. And then let's look at this result. So now if we take this just over this and then plus that over this, we can make it be this. And so essentially we're going to multiply and divide by sigma x squared. And then that we can form this and that. And so then we look at this piece here and we multiply and divide by sigma y squared. And then we can form this quantity. And then in limit, we know that this ratio goes to 1. This ratio goes to 1. And so this goes to alpha, and that's 1 minus alpha. So we're left with alpha plus 1 minus alpha, which is 1. So this converges to 1. And so we're going to look at this in a second. And so really what we're setting up is Slutsky's theorem again. We have a ratio that converges to a standard normal. And then we're going to have something that converges in probability. So now let's look at these two ratios again. This here we showed converges to a standard normal, and then we showed that this converges to 1 in probability. So this denominator cancels with that, and we're left with this. And so this converges, not this, this right here converges a standard normal divided by a 1 in distribution. That's Slutsky's theorem, which is a standard normal distribution. And so we use this quantity and it converges to a standard normal. So that tells us that this piece we can write a probability statement. The probability that this is between, the alpha over 2 cutoff on the left and alpha over 2 cutoff on the right is this probability is 1 minus alpha. Now here we can, if we multiply this up to both sides, subtract the x minus y bars to both sides, and then multiply by minus 1, you come up with the difference of these population means, but the probability of these population means between these two endpoints is 1 minus alpha. Well, these two endpoints is this interval here. So this is a confidence interval. This is the 1 minus alpha % confidence level. And that's what we set out to prove. So we're finished. And that's, but there's one thing I want to mention here. In the next video, we're going to look at Welch's approximation to this setting. And it's pretty fascinating and ingenious how they came up with this. But what they will do is they will use this pivotal quantity and find an approximation to it. And the way they do it is, well, this is a standard normal. And if this bottom part was the square root of a chi-squared divided by its degrees of freedom, then this quantity would be a t-distribution. But clearly this is not a chi-squared divided by its degrees of freedom. But he noticed that it's sort of close. So if this were a chi-squared divided by degrees of freedom, what would the degrees of freedom be? So what he looks at is the first moment and the second moment of this statistic, and then equates them to a chi-squared with, divided by its degrees of freedom, and then finds this nice approximation. Well, anyway, that's the next video is I'm going to derive Welch's approximation. So hope you enjoyed it. If you did, please like it and subscribe so you don't miss the next one. Thanks. Bye.